So of course I stayed up all night thinking about this whole idea of entanglement entropy and the uh, anti-de Sitter space curvature. So I was thinking, okay, so yeah, so we have this Moiré lattice, and we have this 1.1 magic angle. Now, how the heck is that going to correlate to quantum states? Well, let's say we have our U1 little quantum state over here, and I converted it into spherical coordinates. As you can see, we have a sort of a length here, radius r. And then we also have an angle associated with that. This is sort of telling you what the quantum state it is in, and that gives us the quanta or the energy, h bar w, how fast it's spinning around here, and giving us all the different superpositioned quantum states. And then we also have this sort of a tilt to this, which gives us a phase angle. And um, and if you have two quantum states here, well, you could see how there could be a slight difference between these two phase angles. And ideally, you know, once we get to the phase angle difference of zero, we essentially have um, maximally entangled states, right? But around this magic angle of about 1.1 difference, if the difference between them is very, very small, then we still have an extreme curvature here. It's just that we would have an event horizon where, not even light can escape this, right? And in fact, these two things are actually photons right here. It's a U1 representation. It's just a photon. So we kind of have two photons right here. So we're already thinking about light and how light is actually bending towards each other or away from each other, right? Depending on what the phase angle is between these two um, photons. And so we can definitely see the effects of gravity uh, in the interaction between these two quantum states just simply by the phase angle here. As these two progress over time, um, these states seem to approach each other uh, just simply because of this phase angle here. Um, so that's interesting, and it seems that we would have to rotate this phase angle over time and potentially even and cause obviously once you've sort of like the effect of gravity is to like literally make you change the phase angle, really, is it's forcing you to change that phase angle. And what's interesting is that this state here, as you change the state inside the like a superposition of states here, notice how that doesn't really have an effect on the phase angle. So it's like the gravity is kind of this like fixed thing in the quantum realm here. And so uh, really this gravitational change has to come elsewhere. That's kind of interesting how it's not affected by time here. Uh, Although remember that we did represent, like there was a theta here which were represented as WT. I'm sure we could do the same thing here and represent this by another type of WT, which might be something slightly different. But this is exactly how we're able to calculate this in entropy. Once we sort of have the phase difference between these things, we have to take the trace, and then we get this density matrix over here. So we take the trace of the density matrices based off of the phase angle differences between these. And there's a whole bunch of calculations. It gets really intense over here, but sort of got lost there. And I was thinking, what the heck is area? I'm still not really exactly sure what this area is all about, uh, but uh, but I can definitely see how this magic angle can actually form singularity. Well, not event horizons. Yeah, event horizons are the magic angles in the ADS-CFD, and we're talking about gravitational and stuff like that. So that is fascinating, fascinating, fascinating. I definitely stayed up all night trying to think about this because it was just like kind of mind blowing. But yeah, so anyway, this is just one of the cheat sheets that I have. If you're interested in downloading one of these specifically for mechanics, physics mechanics, you can go to freephysicsmap.com and you can download one of these for free. So that's pretty awesome. Anyways, thank you so much